let's move on to networking futures, presented by Darren Harkins, who is a solution architect for NVIDIA. Welcome, Darren. How are you today?
I would be even better if I could work out how to get the mute button off of and working. Hi, guys. I'm hoping everybody can hear me and everybody can see a nice black screen covered in green writing.
I see the slides. It's not in presenter view, but
that's fine. I do apologize now. I'm very much a hand waver. I like to draw on slides. I love whiteboards, and I do realize that this sort of presentation sometimes makes that a little bit difficult. So I'm going to do my best to do the best of both worlds here.
It's in your hands, Darren.
Thank you very much.
Thank you.
Right. So short discussion, mainly a monologue, unless people want to kick in, on looking at large-scale compute topologies. As we head towards exascale, where we are today, where we're going. I want to look more, rather than just chasing a Limpac number, just chasing exa out of a Limpac file, what actually makes a cluster and the interconnect usable, workable at scale as we move away from homogeneous compute, also looking at different ways of linking things together, try and aid the deployment of a flexible workload into a large system, potentially one system with lots of solutions, multiple solutions, whether that's one system in one place linked together, or as Martin may have alluded to, separate systems providing an exa resource, all with the idea of giving the best possible science outcome to the research community, making it usable, making it flexible, making it something that actually can be used for one program to thousands of small programs, all running on a single physical resource. So I'm hoping that makes sense. And this is pretty much where we are today. A petascale type system generally looks at an island of compute, some storage to get the data together, some sort of accelerated compute, usually GPUs, but again, as been alluded to, we could be looking at tensor processing units, we could be looking at FPGAs. There are lots of things that come under accelerated compute, but most of it's linked together with some sort of network. And this is where we want to get to. Now, does it make sense just to scale things up like this? Can we just move from petascale, from one machine that can do a job very well, to just basically a larger machine in the same way? Now, I'm going to say probably no, because I always think of it as doing it from this sort of way. Looking at the statue of David today, it's about 4.5 meters tall, petascale. And you want to move up to something 1,000 times bigger. And just by sheer coincidence, the Colossus of Rhodes was 33, 34 meters in most descriptions. So if you do that 10 by 10 by 10, you're looking at about 1,000 times bigger. And you really couldn't just do that. You couldn't just build up from what you have today to the future. It doesn't really work. So let's go back. We're looking at petascale today. Is there a better way of moving up? Well, maybe. And this is what I want to talk about and to try and get people to think about as we move forward to exascale. Is not just one big machine to solve one big problem. That's not necessarily the UK science way of doing things. We have lots of problems. We've got lots of users trying to solve those problems. Maybe we need to look at a big resource with lots of little bits inside it, lots of ways of linking things together that makes sense, but makes things more usable. And this is going to be part of the drive up to exascale, is not just the software, the benchmarks, the hardware, but also the way of layering all of this together in a way that works. Okay. I want to break away from this for a little bit and just look at what that actually means. I'm going to focus on the interconnect because it's what I know best. And here we have a very simplified factory. We've got some switches at the bottom, some nodes hanging off the bottom of that. Switches are linked together to some higher layer. And then there's something right at the top that could be a higher level factory. It could be linking lots of other bits and pieces of factories together. There are lots of ways of looking at this. But what we've got is the compute sitting at the bottom actually doing the job. And we've got ways of linking it together. And then there's some sort of software or scheduler or something linking all this together to make the jobs usable. Okay. Now we can just chase a number. We can provide an exascale system, a petascale system that runs LIMPAC. It runs it very well. And you get a one with lots of zeros off the end of it on the performance, and you get a little medal, or you get your entry in the table. But that's not necessarily going to give you good science. It's not going to give you the solution that you're looking for, as in ways of actually solving problems, showing that we're doing what we need to do to the research community, and actually getting science out of the back of the system. So maybe we want to look at something a little bit different, which is running lots of smaller jobs on a big system and how that actually works, how that actually holds together. Okay. So the first thing we do is we take the first few jobs off of the queue and we drop them onto the system. It shows like this. We've got 4 jobs running, 8 nodes each. This is the way we spread it out. Everything's good. And for the first few seconds of running a large system, everything's nice and happy. And a job ends, we free up some resource, and the next few jobs drop onto the system. Everything's still really good. Everything's still really happy. Jobs end, jobs start. Now, some of you may have noticed as we moved between those two slides, there's a nice green 8-node job that's just appeared at the bottom here that is massively suboptimal. This job is running on 8 nodes that are very topologically close to one another. Okay. The 8 nodes in the new job are not topologically close. They look as if they are, but if you actually follow the path between them, you have to go all the way up to an external layer and all the way back down again. This is going to slow things down considerably for that one job. And as we scale up, as we get bigger, there are going to be more of these islands, more ways of creating problems between different parts of the fabric. Okay, and we'll have a look at that in a little bit of a clearer way. Say these 2 little jobs finish here, and we run a new job. This job is very clearly suboptimal. It's quite a distance apart topologically, and all we're looking at here is a very small fabric linking a few numbers of nodes together. Okay, so linking those 2 thoughts together, where do we come from? Where do we get to? And how do we scale this up? How does it make sense? So we started here. We started with a petascale system that's well understood. It's got some compute, it's got some acceleration, it's got some storage, and it's got networking linking it together. Going up to something big, we've just shown it doesn't necessarily work very well. We want to go somewhere else. We want to link things together in a slightly different way that makes sense at very large scale, rather than just chasing the number. Okay. I'm hoping this is interesting. I'm seeing very few questions come up, so forgive me if it isn't, but I think it's very interesting and a way of looking at things. What I want to look at here is different ways of linking things together in the same system. Okay, different types of interconnect within the same system, linking nodes together in a slightly different way to be optimal for lots of different science jobs in a way that makes sense, that is scalable, that can grow from a small number to a large number of nodes for jobs that work that way, where we have an interconnect heavy section for lots of jobs that need to talk together much more than is normal. And I'm thinking very much here of accelerated jobs or machine learning jobs, where the interconnect is heavily used. And of course, you have jobs which are interconnect light. I'm going to be slightly rude about the bioinformatics side of things here, but jobs where you load something up at the beginning, the nodes don't necessarily talk to one another very much during the actual job run, and they save some data at the end. Okay, these are 3 different ways of layering jobs together that can be done on one single monolithic interconnect. But why? Why would we do that? Would we not be better to take the benchmarks, to take everything that we're learning from the Excalibur project today and layer that in a slightly different way? We're building or looking to build a really big machine here. Can we put parts of it together in different ways that make sense for these 3 example workloads? Okay. We still, of course, need to be able to run the big job. We're chasing potentially here very large science or a number to get out at the end of it on impact to give us the score. But we also want to be able to run the smaller jobs. And having different parts of the interconnect defined for different parts of that job, to me, makes an awful lot of sense. Why just scale up what we do today to something bigger? Why not learn from what we're learning from the benchmarking, what we're learning from the different sections, what we're learning from different ways of interconnect together, and link that together in a way that makes sense, both linking into the job scheduler, but also into different parts of the interconnect, different parts of the cluster. So you have different types of compute linked together in different ways. You have different types of compute linked together in the same way. And you have a bunch of x86, some in scalable, some in interconnect heavy, some in interconnect light. At exascale, you can carve up the inside of this machine in lots of different ways to do exactly this. And you can run scalable jobs on your scalable section, interconnect heavy jobs in interconnect section, interconnect light on your interconnect light, but you can also mix and match in a very clever way. So if something's interconnect light, but you don't have any space, you can still run that in your scalable section. Okay? But you're not just limited to having sections, single sections of the same. You could have multiple scalable sections which scale both internally and between them. So you could have a scalable section running cloud scale, a secure section running secure scale, but then lots of scalable sections linked together for very, very large jobs. And the same for the interconnect heavy, linked together in a strong way, some of it secure, some of it cloudy, but all lots and lots of heavy interconnect link them together. And again, for the interconnect light, that's even easier. A few cables linking the light together, all linked into different storage models. And again, this is taking it out of the compute, adding storage into the multiple conversation here. You can have storage that's secure and linked into a specific use case. You could have storage that is secure, but can go into the cloud. General storage that can talk to anything. And additional storage islands that can be very fast or very light, depending on the need. Okay, slow spinning Rust for stuff that's going to be archived, or tape for stuff that's going to be archived. Very, very fast Flash or NVMe over Fabric for stuff that's going to be dumped into compute very, very quickly, or for AI. Okay, so what I'm trying to encourage here are different ways of thinking at scale, to step away from the idea that the network has to be exactly the same everywhere to allow it to work, to map the interconnect model to be different at different points, to be heterogeneous, the same way that we're looking at compute, and the same way, hopefully, that we're looking at storage to be like this, to separate everything down. Okay. Hopefully, what we will end up then with is a interconnect linking together compute islands in a way that is scalable from very, very small and very interconnect light to very, very large and interconnect heavy across an entire exascale resource, but without just building up from what we have today and expanding it like a balloon, to move from the David to the Colossus. Okay, so I'm trying to encourage people here to look at things in a different way, to look at the interconnect as not having to be the same everywhere, and to allow people to think that we can have bits of an exascale system that are cloudy, bits of an exascale system that are secure, bits of an exascale system that can link together in a very, very large way, but not just having one big system. It's lots of little systems linked together into a resource that gives you the best possible science in a way that is built up from everything that we're learning today from Excalibur, everything that we're learning today from the pre-exascale systems, and everything that we're learning from the different science deployments that we've got out in the real world. Okay, as a thought experiment, as a way of looking at things, just to derail what everybody thinks of as normal today, and look at something new, look at a different way of doing this, and try and be more flexible, and to get the best possible science out of these systems in a way that makes sense for the best amount of money. Okay, guys, I realize that was very quick. I hope that's engendered some ideas. We're always here to answer any questions that you have on this. Everybody's always very happy to answer questions. So I see there are a couple of bits and pieces that have already come through in the chat. So I'm going to go through those and then open it up to wider questions. Okay. So the first job I see there is from Cliff. Bioinfo jobs do have extra need for individually needing fast access to shared storage. I absolutely agree. But it tends to be point to point. You would have a pile of storage that is linking into each of the compute nodes to load up your job. And this would give you that flexibility to do this, but without limiting the whole system to being the same model. And that's what I'm trying to sort of get across here is we have a big resource here. Do we want to necessarily limit one part to match one person's job and not then have the flexibility to do another job in a slightly different way? And I hope that actually links into Sean's question here, which is, unless this network is software configurable, you risk underutilizing parts of the cluster dependent on the use cases running or underutilizing resources. To a degree, yes. Just simply looking at three models we have here for highly scalable, for heavy interconnect, and for interconnect light. Okay, there could be more models, ways of doing this. There could be fewer. 3 is a good number for modeling this today. And what I hope I showed on the slide 25 is, yes, you can drop a lot into scalable and scalable becomes clogged up. But you can then drop scalable jobs into the interconnect heavy because you have resource there which is over interconnected for your scalable job. You can do the other way around. You can take an interconnect light job and drop it in the scalable. So you always have an upscale. You can take interconnect light into scalable. You can take scalable into interconnect heavy. Okay, so you have a lot of flexibility there, as long as you have a clever scheduling software. You don't necessarily need software configurable networking. You need a very clever scheduler to allow this to work. Okay, this is close to the Phoenix architecture. Yes, it is. But it is different to what we'd normally look at today when we're talking about a mid-scale, I'm going to use the word mid-scale system for a petascale system, which is you've got one interconnect that looks exactly the same everywhere. We could do the same moving forwards. There is absolutely no reason not to. You can have a big interconnect where everything's connected in the same way. But is that going to match your needs? Is that going to match the best resource for the funding available? Or do we want to be flexible? Do we want to look at something different? Do we want to look at different ways of doing things? Okay. I have another question here, which isn't in the open chat, which is, would adaptive routing help here? Again, the answer is very much going to be yes. More because of layering these things together into a large scale fabric with lots of smaller islands of scalable or heavy or light will require a spine or an interconnect or a mesh layer sitting between those, which has the flexibility to define resource as you grow up. Okay, adaptive routing is something that would be massively useful here, again, depending on the topology. I've tried very much to stay away from specifics on topology, specifics on way of linking things together. You have to come up with something, which is why I use the factory as an example. But yes, if you're looking at smaller islands of interconnect, each one of those having smaller islands of compute hanging off of them, whether that's accelerated compute or standard classic compute or even storage hanging off of these, the way you link those together becomes very important. And then the traffic flow between them and secondary routes between those islands becomes very important indeed. And adaptive routing within the interconnect, more intelligent interconnect, the ability to move even some of the compute into the interconnect is a really big feature of a a communication layer at this scale. Okay, it's beyond now. I'm going to draw a really bad picture here. I do apologize to everyone, of having some sort of interconnect sitting in the middle and having some sort of compute sitting around the edge of that interconnect. That's done really well to date. But moving forwards, it's probably not going to give us expand too much more, because if you're moving from here to here, you've got a big blue space in the middle where nothing's happening. If you're moving from here to here, green to green, again, sorry for the bad drawing, then you've got less blue space, but you can't guarantee that's always going to be where you're going. So the ability to merge compute at the edge to compute in the middle, to move networking from the middle out to the edge is going to become more important as we go in scale. The ability to move packets around in a clever way, to adapt the network to the type of traffic that's going on, and adapt the storage communication as well, is probably the key to success as we grow. Having a shell of compute around an interconnect with little nodules of storage on has worked very well up until this date, but is that going to be useful moving forwards? I don't think so. And I hope this just gives a bit of an idea of what is possible moving forwards, why we need flexible interconnect, the same way we need flexible compute and flexible storage. If we're going to make one of those heterogeneous, let's do everything the same way. Let's look at flexibility at every single layer. Let's start blurring the lines and see how this can give us the best possible science for the smallest possible buck as we move forwards up to this sort of scale. I see a hand raised actually from Mark. Is there?
Yes. Thanks, Darren. That was a really, really interesting talk. And you've touched on some of the things I was going to ask, but I just wanted to come at it from a slightly different way. Going back to the idea of having your kind of islands with differently configured network. If you were trying to run a job that crossed all of them, so you said about having an intelligent scheduler that can put it in the best configuration. You've talked about adaptive routing, but if you're running across all of these, load balancing will become an issue, because otherwise some parts will be, you don't want to be underusing the compute in the interconnect light part because it's waiting, in the interconnect heavy part because it's waiting for interconnect light. You'd like to be moving tasks around. So is that a network? That sounds like more than just a network, or that'll be redesigning the applications as well to do that.
Well, this is another thought of these jobs today. Oh dear, right, okay, now I'm going down an interesting line for me, which I hope isn't too out of it, which is these jobs today run on bare metal, and we're looking at ways of optimizing that in exascale. How about we look at something slightly different, which we take one of these interconnect heavy jobs, and rather than stick it on a number of bare metal servers, we actually stick it in a number of containers. And those containers can then be picked up and thrown around whilst the job is still running. Yeah. This is a whole other level of discussion. It's something that we've been looking at of not only can you have an intelligent scheduler that can start a job, how about something intelligent that can pick up a job and throw it around and optimize it mid-course?
Yeah.
We can kind of do that with VMs today, where you take a VM off of one small machine and throw it around somewhere else. You can migrate it mid-use as well as closing it down and moving around. Can we do that with a massive, great big multi-node interconnect heavy job running on bare metal? No. But how about we stick that inside a slightly smaller, very thin box, and we can pick that up and throw that around? Well, we can do that today. And the architecture is there to do it today. But does it work? That's a whole other thing. Can we pick it up on a big scale, move it around, move something from this node and put them on these two, So we then have a resource of 4 sitting over here. Is that something we can do? Probably. Is that something that would make me very nervous today? Absolutely. Are we working towards that? Of course we are. But all of these things come at another level of complexity outside just talking about topology and compute. And we're now blurring the levels between those. And I am very, very happy to have that discussion with absolutely anyone around what we can do with containers and how we pull that out of the hardware, how we move things around, and how we might link that into some intelligent data processing units on the interconnect. Mm-hmm. Okay. Mm-hmm. I see a comment there from Sean. Currently issues around MPI and containers. Yes, absolutely. Of course there are. There is overhead, and this will come at a cost. Everything comes at a cost. Whether that cost is the job slows down, or you throw more dollars to get a solution that allows you to do this, mm-hmm. or you accept the fact that you're not going to be able to do that, and the cost is that you can't move these jobs around. Everything comes at some sort of cost, whether that's in flexibility or dollars. So yeah, you're absolutely right. It's not ideal, but maybe by adding in more intelligence to the design, it's something we can design in to minimize the cost of overhead or the cost of dollars to be able to do this on a very, very large scale machine. We're never going to have a solution that's optimal for everybody on something that's this big. Is it possible that we can, the greatest good for the greatest number? Then probably yes. But that's a very, very long and interesting discussion that we've got between now and when we start looking at pre-exascale and exascale machines. Okay. Guys, I hope that was interesting. I see we've come to the end of, exascale should be long-running jobs, so moving around probably gets... I can't disagree with you on exascale if you're using exascale just for those big long-running jobs. But is that all this resource is going to be used for? Are we going to be filling in the little gaps with little things? Or are we going to tell people they can just run big jobs on this machine, and for little stuff, they have to go elsewhere? Guys, I hope that was useful and interesting. I hope I wasn't just ranting to an empty screen. Thank you so much for the questions. I really appreciated them. Anything more that we can talk about, you always know where we are, and we're happy to have any of these discussions moving forward.
Darren, thank you so much. A great presentation. Love the drawings. Good conversation by everyone. I really appreciate that. And Darren, you took the load off me. You took the questions head on. So thank you very much. Appreciate having you.
You're welcome, guys. Thank you.